Hello, our science students. Welcome. We are going to continue our work in deformation, and we're going to work on page 3. That's activity 4, page 3. Motion along the San Andreas. How do our GPS sites help us see what deformation might look like along the San Andreas Fault as plates move? San Andreas is the boundary between two tectonic plates, the Pacific Plate on the west side and the North American Plate on the east side of the fault. Here's the Pacific Plate, here's the North American Plate over here, kind of mostly over land. The code below is set up to show two GPS stations on the map. One station is on the west side of the San Andreas Fault and the other is on the east side. We're going to run the code that is currently in geocoder. So you can see that the code's already there. We're going to hit run, and you can see that two stations appear right here. We need to get some information from those stations, and so we can click on those stations like this, and it'll tell us the station ID, latitude, longitude, and most importantly for us right now is the speed and direction. So let's scroll up here. So in question 10, it asks for the speed and direction of 513. So let's go and see, do we have 513? Yes, we do. We clicked on 513, and 513 has a speed of 46.3 and a direction of 320. So we can put that in question 10 right now. 46.3 and 320. You can do the other one. You simply click on the station and you get this information and plug it into question 10. Now we need to use the information in question 10 in our code. So we want to go to the deformation category and pull that out. Go to data and drag out 4 number blocks. Put the number blocks in the deformation block, and then we'll figure out what we need to do from there. So deformation, pull this out. Leave all the red code there. We want to pull out 4 number blocks. So to set up this code, I went to deformation and I picked out the deformation block here. Then I went to data, I pulled out 4 of these numbers. I plugged them in, and in the first 2 number blocks here, I put the speed and direction for plate 1 that we found here. It's also right here on the map. We clicked on 513, P513, to get that information. You can click on the other station and get the information for the other station, and then click run, and it's important that you click over to deformation to see your deformation. Once you've finished coding, you can do questions 12, 13, and 14, which are about how the plates are moving relative to each other and where in California the plates are moving most quickly and would have the most deformation over time. And down here, you really want to explain your answer in question 14 to the multiple choice question in question 13. If you, for example, if you say Avenal, then you need to explain why you think Avenal has the most deformation. Now we're going to move to page 4 in activity 4 in assessing seismic hazards. The San Andreas Fault is 800 miles long, stretching the entire length of California. On this page, you'll investigate 3 different areas and compare deformation in these 3 places. Using your GPS data, you'll investigate whether these locations are experiencing the same amount of deformation. So in question 15, explain how you would use deformation simulation to investigate and compare the deformation between pairs of stations pictured. If you can use some coding language in your answer to this question, I'd be really happy. Think about what blocks you'd use, how you'd what data you'd plug into those blocks. That would be great. Or if you just want to overall explain how other people might do it, that's okay too. We are going to look at 3 different pairs of stations here and see which one has the most deformation. So we can go back to using our deformation block, plugging in 4 data points, and checking the 3 different triangles that result to see which one has the most. I'll do the first one for you. So you can see in the coding area, I've pulled up the deformation block, I've gone to the data block, and pulled out 4 number blocks. Now it's our job to put data into those number blocks. That data is going to come from these 3 sets of GPS monitors for the plates. So the first monitor has a speed of 38.7 millimeters per year, so we can plug in 38.7 for plate 1. We're going to use P182 as plate 1. Plate 1 also has 327 degrees. You can see where I got that information. 38.7 and 327. For plate 2, you can pull the information from PS263, 19.8 millimeters and 322 degrees. Remember vectors, we were talking about speed and direction. The speed here is in millimeters per year and the direction here is in degrees. If you have speed and direction, you have velocity. So just to help you remember, when we're looking at deformation, we're looking at the velocity of the plate, which includes both speed and direction. Velocity equals speed and direction. It's different than just plain speed. Speed, you don't know where you're going. You know how fast, but you don't know where. So velocity has that extra element, its direction. So I put in the data for the first 2 stations, and I'll run my deformation here so you can see what it looks like. One plate is moving faster than the other, and they're moving in slightly different directions here. I'm going to take a screenshot of this information so I can compare it to the other 2 sets of stations when I run them. Now that I've taken a screenshot, I can enter other data from the other 2 sets of plates, the other 2 sets of monitoring stations, the GPS monitors, and put in 46.3 millimeters, 320 degrees. So erase this data and put in the new set of data. So 46.3 and then 320, and then you'd have to go down and reset this one as well, 16.5. I think you get the idea. And then run that, take a screenshot, do this data and take a 3rd screenshot. Compare your 3 screenshots and figure out which one has the most deformation. Once you figured out which 2 sets of monitoring points, GPS stations, have the most deformation, you can answer questions 17 and 18. Make sure you use some good evidence for question 18. Look at those screenshots and figure out how you're able to tell which plate has the most deformation. And then based on these stations, where is the San Andreas experiencing the fastest buildup of deformation? If you scroll up to the top of the page, there's a map here with where the stations are. You can see the 2 sets of GPS stations in Northern California, Central California, and Southern California, and look at your deformation data to decide which is experiencing the most deformation or the most change between those 2 plates. Thanks for watching, everyone.